want to come up with a rule for taking derivatives of powers of x. So just have these three examples that we'd like to figure out. Now in each case we're going to calculate the derivative, which is going to be based on a limit. So in this first case, if our function is x cubed, they're going to need to take the limit as h tends to 0 of, let's see, if this is the function that cubes things, if you give it x plus h, it's going to cube that. So there's f of x plus h, and then f of x is simple, it's just x cubed over h. To do this derivative, we're going to have to take a similar limit, but instead of having x plus h cubed, we'll have x plus h to the fourth minus x to the fourth over h, or in general, if we want to take the derivative of x to the n, we're going to have to take the limit as h tends to 0 of x plus h to the n minus x to the n over h. You can see in all of these cases, the tricky part is going to be, well, it's not necessarily tricky, but it's going to be sort of the time-consuming part, is to figure out to expand this so that you can collect like terms. So we need to expand these binomials. And there's something that can help us called the binomial theorem. So let's look at that. The binomial theorem, if you had something like x plus h to the 0, obviously x plus h to the 0 would just be 1. If you have x plus h to the 1, you have 1x plus 1h. Now if you look at this, if we want to do x plus h squared, what we're going to have to do is we're going to have to multiply x plus h times itself. So we're going to have to take x plus h times x plus h. That means each of these terms is going to get multiplied by an x, and each is going to get multiplied by an h. When this term gets multiplied by an x, you're going to get 1x squared. When this term gets multiplied by an x, you'll get 1xh. Then this one will get multiplied by an h, and that will give you another xh. So you're going to have 1 plus 1 is 2 xh's. And then finally this last term will get multiplied by h. That's going to give you 1h squared. Now watch what happens if we do it again. So we're going to do x plus h cubed, which means we're going to take each of these ones from x plus h squared and multiply it by an x, and also multiply them by an h. Now when this first one gets hit by an x, it's going to make 1x cubed. And then when this, let's see, when this second one gets hit by an x, we'll have 2x squared h. This term will also be multiplied by an h, so we'll have an x squared h plus 2x squared h. 1 plus 2 is 3x squared h's. When this one gets hit by an h, that's going to make 2xh squared. There's also going to be, when this one gets hit by an x, that's going to make another h squared. So 2xh squareds plus another xh squared make 3xh squareds. And then finally this last term will also get multiplied by h, so you're going to have 1h cubed. And now let's do x plus h to the fourth. To get x plus h to the fourth, you just have to take x plus h cubed, which is the same as this, times x plus h, which means multiply each of these by x and multiply each of these by h. See, you're still going to get 1x to the fourth. Now this is going to get hit by an h, and that's going to get hit by an x. 1 plus 3 will make a total of 4x cubed h's. When this one gets hit by an h, and that one gets hit by an x, you're going to have x squared h's. You'll have 3 of them, and 3 of them make 6x squared h squareds. When this gets hit by an h, and that gets hit by an x, when we combine the two, we're going to have xh cubes, right? So we'll have 3 plus 1 will make 4xh cubes. And finally, when this last one gets multiplied by h, we'll have 1h to the fourth. I hope you're starting to see the pattern here. So what's happening is, since each thing is getting hit by an x and getting multiplied by an h, then there are terms that can combine. So what I can do, I can figure out the coefficients pretty easily. Let's go to the next one. X plus h to the fifth. Let's see. We're going to have 1x to the fifth. 1 plus 4 is 5. X to the fourth h's. 4 plus 6 is 10. X cubed h squareds. 6 plus 4 is another 10. X squared h cubes. 4 plus 1 is 5. X h to the fourths. And 1 plus none is going to be 1 h to the fifth. So you may recognize this pattern here in the coefficients is called Pascal's triangle. You have 1 and then 1, 1 and 1, and then 1 plus 1 makes 2, and 1 plus 2 makes 3, so 3, 1, 1 and 3 make 4, 3 and 3 make 6, 3 and 1 make 4, 1 and nothing make 1 again. So in each case, the number is coming from the sum of the two above it diagonally. So this 1 is coming from 1 and nothing, so it's still 1, or this one is 1 and nothing is still 1. So we get this triangle called Pascal's triangle that gives us the coefficients. As far as the terms go, whatever power you have here, that's going to be the highest power on the first variable, right? So it'll be the fifth. And then in each successive term, the power on the first variable goes down, and the power on the second variable increases by 1. So we have 5x's, no h's, then we get 4x's, 1h, then 3x's, 2h's, and so on until we've got no x's and 5 h's here at the very end. So that's very handy. Now I just want to point out one other thing. If you have x plus h to the n, you can see that there's a match here. Whatever this highest power is, that determines the highest power on x. Also, it determines the next coefficient. If you have it to the fifth power, the next coefficient is 5, or there's a 4. Okay, so even though it would be difficult to think about what does this triangle become when you go down n levels, you can at least tell what the first two terms are going to be. There's going to be an x to the n, and then the next term is going to be n x to the n minus 1 with 1h, and then there'll be other terms, and each of those other terms is going to have it, let's see, I was going to say stuff with at least h squared multiplying it. Okay, so if you do it to x plus h to the nth power, the first two terms are pretty clear. It's a little more complicated for the rest of the terms. There is a formula that will do it, but you can see that the rest of the terms here are going to have h squared, h cubed, so at least h squared is a factor of the remaining. So let's go back and see how that can help us with our original problems. So we wanted to find the derivative of x cubed, and we knew that that would be the limit as h tends to 0 of x plus h cubed minus x cubed over h. But from the binomial theorem, or using Pascal's triangle, we can expand that pretty quickly. We get x cubed plus 3x squared h plus 3xh squared plus 1h cubed minus x cubed all over h. With a little simplifying here, we have the limit as h tends to 0 of, because there's a minus x cubed to cancel that leading term, and there's an h in everything else, we can pull out that h. We're going to have 3x squared plus 3xh plus h squared all over h. Of course, h is now a common factor of the top and bottom, so let's cancel it. And we'll have the limit as h tends to 0 of 3x squared plus 3xh plus h squared. Of course, this limit, to the limit of the sum, each of these terms is going to disappear because as h gets smaller and smaller, it will wipe out the 3x and the h squared. All that's left is 3x squared. So we've just shown, by working with the limit definition, that the derivative of x cubed is 3x squared. Let's go to the derivative of x to the fourth. So the definition of this derivative is the limit as h tends to 0 of x plus h to the fourth minus x to the fourth all over h, which, by using the binomial theorem to help us expand here, we're going to have x to the fourth plus 4x cubed h plus 6 x squared h squared plus 4x h squareds plus xh cubed plus h to the fourth, and then minus this x to the fourth, so all over h. Of course, the negative x to the fourth and the positive x to the fourth are going to cancel, and there's an h in everything that's left after those two are gone, so I can factor that out. So we'll have the limit as h tends to 0 of h times 4x cubed plus 6x squared h plus 4xh squared plus h cubed, all divided by h, and of course those h's, being common factors, cancel. So we just need to find the limit as h tends to 0 of 4x cubed plus 6x squared h plus 4x h squared plus h cubed. And each of these limits, each of these last three is going, h cubed, sorry, each of these last three is going to 0, so those will all disappear, and we'll be left with just 4x cubed. Notice that this one doesn't depend on h, so it doesn't care what happens as h goes to 0. So the derivative with respect to x of x to the fourth is 4x cubed. Now let's go to the more general problem, where we need to find the derivative of x to the n. So we're talking about taking the limit as h tends to 0 of x plus h to the n minus x to the n all over h. Now, we know from what we looked at with the binomial theorem that this is going to be x to the n. The next term will be n x to the n minus 1 with 1h, and then the rest is going to be stuff times h squared. And then we'll have this minus x to the n is still there, all divided by h. And so we said, we don't know what the other coefficients would be. That's a little bit tricky to figure out, but we can tell that it's going to be stuff that has at least h times h in it, right? So after the term that has 1h, then the number of x's will decrease, and the number of h's will increase by 1, so you have h squared, and then h cubed, and so on until you get h to the n. Now again, we can see that there's going to be an x to the n and a minus x to the n, so the limit as h tends to 0. Let's go ahead and factor an h out of all of these things. If I take an h out of this first term, I've got nx to the n minus 1, plus, if this stuff all has h squared and you factor out 1h, now you have a bunch of stuff that has at least 1h in it. Had at least h times h, now it has just 1h at least. Okay, so now the h's cancel, and we have the limit as h tends to 0 of nx to the n minus 1 plus stuff times h. Well, this stuff is not infinity. It's going to be some finite value, and most of it's going to go to 0. But if you have stuff times h, and h is going to 0, then by the product rule for limits, you're just going to get nx to the n minus 1 plus stuff times 0 would just be 0. So we've just shown that the derivative of x to the n is n x to the n minus 1. Now we've only shown it in the case where that binomial theorem applies with Pascal's triangle there. So we've only shown it in the case where n is a non-negative integer, right? It's got to be a nice round number. And it turns out, and we'll be able to show later on, that actually it holds in a lot more cases. So we've only shown that it works when n is a non-negative integer, but it actually will work in all cases. So, for example, if someone asks you to find the derivative with respect to x of x to the 1/2, we didn't really prove it in this case, but it turns out that it still holds, and we will prove it later. The pattern holds. Whatever the power is, when you have a power function, that power will come down, and you'll have x to 1 power less. Now remember, if you have 1/2 and you take away 1, you'd get negative 1/2. So we'd have x to the negative 1/2, or that's the same thing as 1 over 2 times the square root of x, since x to the 1/2 power would be the square root of x, and a negative exponent just lets you go from upstairs to downstairs. So you can actually use it with any exponent. Doesn't matter what it is. So let's say we had x to some strange value, like maybe x to the e. Well, e is still a constant, so we have x to some constant power. That means that this rule applies. The power comes down, and you get x to 1 power less. Very handy rule. Lets us take the derivative of many, many things.